Okay, so far we talk about Nash equilibrium, different concepts like correlated equilibrium, min-max solution concept, or dominant strategies, etc. And we talk about computation of Nash versus correlated versus min-max, etc. And we talk about price of anarchy. Now, this price of anarchy actually has been developed quite a bit. So the first price of anarchy result was the result that introduced by Kotopisius and Papadimitriou in Stacks 99. And this paper and there was got actually the Gödel Prize, because essentially introducing the concept of game theory and the particular price of anarchy that we have seen. What was the price of anarchy is that if you have a Nash equilibrium, what is the situation of a worse Nash in terms of the social welfare comparing to the optimum solution? That is the dictator and that can essentially dictate that which strategy that the people can take. That's what's price of anarchy. Now, in Stacks 19. So this is the paper that actually we have Avram Blom, me, Katerina Liggett, and Aaron Ross in Stock 2008 introduced the concept of price of total anarchy. It was in Stock 2009. So here we consider a bit more general than Nash equilibrium. And we consider regret minimization algorithm that I will talk about it briefly today. This is some kind of learning algorithm which are very useful. You hear a lot, for example, especially at industry, you may hear even that. This paper actually introduced this concept of price of anarchy or similar concept for the concept of like regret minimization algorithms. And this is, you can see actually Nash equilibrium. When you are in a Nash equilibrium, also in terms of the regret, would be no regret at that time. So Nash equilibrium is a special case of essentially this no regret algorithms. So Tim Rockgarden, this, I mean, essentially he was mentioning to me that he was trying to teach this paper that we had. It was actually a paper that was very well cited. The people have used this concept quite a bit. And I will say why these regret minimizations are very important in practice as well. He tried to talk essentially the proof in the class, and he could actually get something more generalized with a much maybe simpler proof, even actually more clean proof. And this is the concept of smooth games or a smoothness. So he could introduce this concept of a smoothness and or a smoothness argument that for not, it is not for everything, but almost all price of anarchies, as well as more general like price of total anarchy that we have introduced in that paper, all of them actually can be obtained from a smoothness argument. So just coming back to these figures, here we have this like essentially pure Nash equilibrium. It may so pure Nash, I mean, if you consider two players, that is easy to compute, but in general it might be not hard, and it may not exist. That is, of course, is a special case of mixed Nash equilibrium. Mixed Nash equilibrium always it exists, but hard to compute. This is this concept of correlated equilibrium that we discussed. It is easy to compute. And finally, this kind of no regret algorithm, which are easy to learn. What is the idea? So how do we reach to a Nash equilibrium? In the Nash equilibrium, you can consider, now if we consider somehow, it is called dynamics of the game. That the people, each of these, we have n players. we have n players. And then each of them, they pick a mixed strategy SI, possibly mixed strategy. And in that case, player I incurs a cost of CIS. Okay, so S is essentially the vector that we talk about. It is a vector of S1, S2 to Sn. This is a strategy profile or vector of a strategy. Each person takes a strategy, and then person I takes a strategy Si. It can be possibly mixed. And then assuming the objective function is the cost of S would be sum of the all I's CIS. So, so the cost of this essentially, the cost of the strategy S or just C of S, we say that this is the sum of the cost for each of these. In general, it is, you can consider the cost of the game is less than the cost of individual, or like essentially this cost in some sense is the benefit of the whole system. For example, we talk about this kind of congestion games. So the congestion game, the cost for everyone was the total average time essentially. Correct? So, and there we consider, for example, the cost of S is equal to CI of S. So there we consider the, like, instead of average, as I mentioned, average and the sum is the same. You can consider the sum of the total traffic, like the time that each person will be in traffic. That would be the one that we try to minimize. Good. So now, what is the definition? This is essentially the lambda mu smooth. A game is lambda mu smooth if for every player Si and for every pair S and S star of the outcomes of the game, and outcome here essentially means that the people taking different strategies. So Si, S is one essentially pair, which is that the player essentially I take Si. S star is the optimum that we will talk about it, but we say that we have two strategy profiles. So S and S star are just two strategy profiles or vector of strategies. We should have this property that if you will sum it up over all I's. So what is this one? It says that if you will the CI, this is the meaning of smooth. It means that between S and star, in some sense, it is some smoothness happening. What's the meaning of smoothness? It means that if you consider a new strategy profile in which only the ice guy, only for the ice guys, I am using the strategy SI star. For everyone else, I was using the strategy that they was in S. Good. So I will sum it up over all I's. What would be the cost of I? For example, the traffic, what is essentially the time that goes from A to B? The only thing is that when I just do this sum on the I summand of this time, I will consider CI of. Instead of, so if instead of this S star, if it was not this star, it was just the strategy S. Here, I'm just replacing the ice component of S from the S star, the same component. Then I will sum it up. Then what is the property that I should have? The property that I should have is this one. If you do this one, then the cost of this, the sum of this, would be at most lambda cost of S star plus mu times cost of S. That's the meaning of a smoothness. It means that somehow, if I combine S and S star, my cost, the total cost, also would be some lambda times cost of a star and mu times cost of s. And this should be correct for lambda greater than 0 and mu less than 1. Good. This is the concept of essentially a smooth games. A game is called smooth if it has this strategy. Good. Now, let me go back before continuing with essentially smooth games and what are the properties, especially about the price of anarchy for them. I needed to also say what is the price of stability for this. Sorry, the price of total price of. But for that, I need to come back here a little bit about the talk about this kind of no regret algorithm. Good. So far we talk about pure Nash, just the cells in a matrix. Mixed Nash, which are essentially distribution over this. Correlated equilibrium, that essentially we have this one, that we have somehow the distribution over the whole matrix. And these are correlated. We cannot write it as P times Q. That's essentially the difference. It's more general than mixed Nash. Now, what about no regret algorithms? And note that in each of them, for example, in the Nash equilibrium, you can think about this kind of best response things, that the people are playing some game, they are playing some strategies. Then I'm doing the best response to them. Then maybe the other people also do the best response to everyone else's things, and they are doing this. This is called game dynamics, such that we hopefully we reach a Nash equilibrium that no one wants to change given the other changes. Now let's go and talk about no regret algorithms. So this is just essentially brief intro such that we can talk about it. So what are the things, because these are all we go to no regret algorithm. And in some sense, the smoothness came out of the paper that we had about no regret algorithm. What is the no regret algorithms here? Let's essentially go through this. So a no regret algorithm, essentially this type of things. So I talk about the dynamics of this Nash equilibrium. Now, the same kind of dynamic you may consider essentially for the no regret algorithm. So a no regret algorithm is a strategy for making a sequence of decisions So we are making a sequence of decisions over a time period that we don't have uncertainty. What is the promise? The promise is that over a long period, we will talk about this long period, the performance would be approximately as good as the single best fixed strategy that has been chosen in the hindsight. So this is a good example actually that we can talk about it. The scenario that we can do. And then I will talk about regret, etc. So consider essentially a daily commute. So you need to choose between two routes, route A and route B. To get to work, and as we discussed, when we talk about these games, we talk about the long period, essentially. So here, we will consider for over a long period. So you want to choose between route A and route B to get to work for 100 days. This is the meaning of long. So you don't know the traffic in advance. You bought the house in this neighborhood. Recently, you want to go from your house, your home, to your workplace. You don't know the traffic. What do? You try switching between A and B and learning from the past traffic. Good. So so here you will switch between A and B, and then you see what was your essentially the total commute time over 100 days total. So the total running time that the total thing that you had, it was 300 minutes. Good. Between A and B, and you will try. Now, what was say the best fixed strategy? So after 100 years, 100 days, you look back and see if you had only taken route A every single day, then your total time would have been 2,800. It means that in this case, your regret is 3,000 minus 2,800, which is 200 minutes. And this is the cost that you paid for not knowing in advance that the route A was the best fixed choices. So the regret is a cumulative difference between your algorithm's performance and the performance of the best single action. And as I mentioned, this is, as we discussed, this is the best single action strategy that you could have chosen in the hindsight. And by best, single best means essentially like still it can be a mixed strategy. There is no need to be pure, but it can be mixed. What is your objective function? You try to minimize your regrets. So in particular, a no regret algorithm means that the algorithm's average mistake or loss per round gets closer and closer to zero as time goes. This is the type of algorithms that we will call it no regret algorithm. And so this is the mathematical formulation. So it says that a no regret algorithm is the average regret per round approaches zero as the number of rounds gets infinitely large. So if RT is the cumulative regret after T rounds, so here this essentially the sum this cumulative regret in that case was 3,000 was your total travel time minus 2,800 if you took the best among A and B, which was, and this was interesting, you just take that one as a fixed strategy. Then it was 200 minutes. So here, for example, this is the, if you want to take the average, would be 200 over 100 minutes, over 100 days. So essentially, so here, if you take the average would be 200 over 100 days, which would be 2. What do we want? We want to have this one, that as t goes to infinity, your cumulative regret over time, the limit goes to 0. That's the meaning of no regret. Now, Why do we consider no regret algorithms? In some sense, the no regret algorithm, so this is the way that is defined. So you try to essentially compare your algorithm that essentially runs and compare the loss or the regret that you had with a best fixed strategy. Note that this is not the optimum. So this is very important. This best fixed strategy is not necessarily optimum. Why? Because we say that, note that how did we compute for A? Say that if you consider if you just took A essentially, and every day you took just A, what was your total travel time? Note that it might be the case in some days, actually, A had some kind of traffic jam or other things, and really A was worse than B. So optimum, possibly it could just alternate between these two. It goes from A to B, from A, B, etc. So if optimum, so now what do we see it here? After 100 days, we see what it happened essentially here. And then we say, okay, if you take the A, it was this. If you took B, we will compare. However, optimum can be better than just fixing A or B, because optimum also could alternate between this. However, this is the issue. You can see that when we try to consider this kind, and this is an online algorithm. What's the meaning of that? Like each day you are taking a different action. And based on this action, you will see essentially some regrets. And then you will essentially consider some of the regrets. So the main important things is that why do we consider this the best fixed strategy? Because we cannot compare ourselves to the optimum. Because this is the online algorithm, optimum. If optimum knows the whole thing, optimum knows each day should take each of them because it knows exactly. So when I go today, I don't know which way is essentially a traffic jam. Maybe now, essentially, thanks to Google Map, etc., you can take it, get some ideas there. But say you don't have that, so you don't know which one is the things. Optimum knows that. But the issue is that because you don't know, optimum knows, in lots of these cases, you cannot compare yourself to optimum. Or if you compare it, you get zero. You can be very bad comparing to optimum. So, okay, in this case, I cannot become essentially comparable to the optimum, but should I have maybe another baseline? And this is exactly this best fixed strategies. That you will take some strategy and you will go this one all over the time. It is some kind of baseline, so that if I knew that in average, I compare with this one. The good thing is that now if I consider this as my baseline, then I can get some good results or some kind of provable guarantee. While if I take the optimum that can alternate between these things, I cannot get any bonds, any meaningful. That's the reason that we consider best fixed strategy. As I mentioned, it is called the fixed strategy in the hindsight. That if you have seen about this, what was the things for A, B, and then you will take it, and you want to be at least comparable to them. Now, so that's the meaning of the no regret algorithms, means that essentially you want to have your regret be equal to zero, essentially. Let me give you an example here. A typical thing that actually is used a lot in practice is the multi-arm bandit algorithms. So multi-arm bandit problem is like a classic problem. And a no-regret algorithm is a solution strategy for this. What is the bandit problem or the multi-arm bandit problem? So it's a typical problem. This is like you will hear a lot, the bandit problem, essentially. for decision making under uncertainty. What is the setup? Actually, let me give you an example. A very good example of this ones. If when you are, for example, seeing short videos at YouTube, lots of this essentially based on the multi-arm bandits problem. What is that? In some sense, what does YouTube try to do that? It try to show a video that you spend the most time on it or you like it. And you start with something, but at the beginning, it does not know what type of short or what type of like the movies you like. But then for each of them, from the action that you will do for each of them, for example, some of these short you pass, some of them maybe you will see several times. From this action, this is very similar to a traffic example, essentially. Understand, oh, you like this type of things better, you don't like this one, and then converges to show the one that you like. There are lots of these scenarios that actually are, even for example, the items that you may see at Amazon for the shopping. Try to find what type of thing you want to do, and it might be different over different times. But it tries to, when you are in one session, it tries to find those that you like the most. How does it understand that whether you click on them or not? So it's a very common thing essentially in industry. And I will say more, like there are lots of studies more at industries. So what is the setup here? You are, say you are running this is a typical example of that. The setup is that you are in a casino facing K slot machines. So, or essentially in this case, it is called one-armed bandit. Each machine or arm has a different unknown reward probability. What is your goal? You have T pools. These are the corresponding to time horizon. You must decide which arm to pull in each round to maximize your total rate. Good. So this is very similar. This is actually, you can see even the, for example, the YouTube example that I have mentioned is a special case of it. Sometimes note that the number of arms potentially can be exponential. It can be very large. So you are essentially the video that I want to show to you essentially. Or you are essentially in the casino, there are casings, and you want to say which one I should play essentially each time. Now, what will happen? So any of these arms that you are doing essentially pulling it, you get some reward. There are two types of bandits. One that is essentially you only see the one that you pulled and you will see the reward for that. There are others that are more general that say that, okay, if you took the other actions, also what was the reward? And these are like the algorithm that works for both cases, essentially. For example, in the traffic time, you can say that after each day, you know, if you take this route versus this route, you knew how much you lost, essentially. And again, each day might be different. There is no fixed path, essentially. But you compare only to a fixed path because you cannot compare more. This is the baseline that the people agree that is actually reasonable. Generally, for these ones, this have this concept of explorations versus exploitations trade-off. This is a similar thing that we have, for example, in the secretary problem. Secretary problem for online decision making also has such a. So the exploitation is that should you keep pulling the arm that has paid out the most so far? In some sense, you are exploiting your current knowledge. Or this is the exploration. Exploration is that should you try a different arm that you know less about it? And in this case, who is essentially the best arm? And again, here we consider the scenario that optimum potentially at each round, it can take the best ones, but we cannot compare with that up. So, okay, I don't know, maybe one of these things at the hindsight, one of them is better. Probably the person who is running the casino knows which one is better. I try to find that arm. That's the whole idea that I try to do that. The same thing is this one, that like YouTube shows you different videos and want to say that, I mean, what is the type of video? This, like, you can consider the vector that how these are, like, I don't know, either action, drama, comedy. There are lots of, and what type of things essentially. There are several vector. Try to understand what type of vector of characteristics of these short videos that you like it, such that it can show us more of. So again, for this kind of multi-arm bandit things, the typical thing is that the regret is defined the same way that we have defined as the difference between your algorithm's total reward versus the reward you would have gotten by playing the single best arm. The one that has the highest probability for overall T rounds. Yeah.
Why do we define the graph as a fixed strategy and not the overall?
So as I mentioned, the overall optimum, we are considering online algorithm. What is the problem with online algorithm? The online algorithm, you don't know which action. The issue is that, and it is irrevocable. As we, for example, see it also in the secretary problem. If you choose this action, then you cannot essentially revoke it. And the problem is that the main issue is that we would like actually to compare it with optimum. That would be a better thing. But in lots of this kind of online algorithm, if you want to do that, you get zero essentially. So your ratio compared to the optimum would be zero. Because essentially optimum can fool you. I mean, optimum has the knowledge. Whenever you want to choose this one, it chooses something that's, and especially if it knows the knowledge about your algorithm and say you know the random bits, etc. Essentially an adversary. You can consider now optimum as adversary. Adversary is the same as optimum in this case. It tries to essentially fool you. Anytime that you try to do that, is know that you want to select this one, I will give the other one as the best thing. And you cannot compare this.
So the optimal.
The ratio of my algorithm to the optimum goes to zero. The reward of my algorithm to the optimum goes zero. So because of that, that's the thing, exactly the one that I'm considering here. I try to consider some kind of the so here, that's exactly the thing that I try to consider, the average regret, which is RT over T. Good. So let's see whether this algorithm actually says talk about this one. Okay. So let me just. So this is this concept of exploitation versus exploration, exploitation of your current knowledge versus exploration of to find essentially gain new knowledge. That happens a lot. And so I don't want to go through, I mean, this is like you can have another class essentially. This is part of reinforcement learning. So if you talk about reinforcement learning, one of the most important one is kind of no regret algorithms and the bandit algorithms. Or RL. This is a very famous thing that now lots of things essentially the robots now they can learn to run based on reinforcement learning. All of them are essentially this kind of no regret algorithm, or essentially bandit problem. Bandit is the one of the most important ones. And for this, there are two famous algorithms. I don't want to go through this one. There are actually three famous ones. It is called epsilon greedy. So epsilon greedy, UCP, and Thompson sampling. All of these algorithms, the epsilon greedy probably is a simple thing. So in the 1 minus epsilon time, you are just using the best arm that you know so far. Good. So you know that, okay, what was the best arm that I had it so far? With my current knowledge, I will just use. And however, in the epsilon time, you will explore new stuff, such that you gain more. There are other algorithms called the UCB algorithms. These are all of them are this type of thing that you try to essentially update your knowledge. So what would be a typical algorithm for no regret algorithm? So say you have these arms, and then you want to select one of these arms. Then, so you know what is the probability, like you know the, for example, let me say essentially for this. So the routing thing that might be easier. So what was this one? So you have several routes that you want to go between A and B. So this is the point A, this is point B, and there are several, different routes that you may take it. And say each time the route between this route 1, 2, 3, 4. So at each time, one of these routes essentially might be the best. Like, what type of, these are the type of essentially this algorithm that, like, from the, you know that each day, what is the probability that this route is the best route? Good. So according to that probability, among the routes that you have taken essentially. Or you can think about this one. Some of the routes that you didn't take it, maybe the probability was 0. It doesn't matter. So in some sense, you have some kind of weights for each of these routes. How good is this each of these routes? Or you can generalize this one also for this kind of multi-arm bandits. That you have essentially some ideas about how good is this arm. You have some weight for them. Now, according to these weights, you will select one of them, some probability distribution, because these weights can give you some probability distribution. Like weight of each guy over some of the weights. That gives you a probability distribution. According to that, you will select the next one. However, this is the important one. After this, you will see after this, okay, I chose these arms. But then it's the simplest case that you see the benefit or the reward of each arms. You say that I choose these arms, but in this case, the other arm was the best. In this case, what do? You are updating the weights. And the typical things that, like, you will, for example, the one that was a good one, you will multiply it by some factor. This kind of multiplicative. That if this was the good thing, you try to increase its weights. Why? Because you want to do it fast. Because if this guy in 4 consecutive runs, it becomes the best, it means that the probability of this should go up. How you can make it up? You just multiplicatively increase, multiply its weight. So it is 1, then it becomes 2, then it becomes 4, 8, and 16. So this is the way that you will, that is the approach that sometimes you can actually find the best arm. Not necessarily with factor 2, but with 1 plus epsilon. But these are the typical algorithms that this kind of this epsilon greedy, as I mentioned, UCB or Thompson sampling, epsilon greedy is doing less. Is the simplest one. The people are using it, as I mentioned. Epsilon fraction of the time you are exploring new options. But the Thompson sampling or UCB, the one that actually Thompson sampling, the people were using it maybe before more, or like that was guaranteed was better, but lots of them in practice, they were using epsilon greedy. This UCB algorithm is essentially the more recent algorithm and actually works very well. Now, this is the state of the art. Lots of essentially people in industry using UCB algorithm. It's a very simple algorithm to do that. Thompson sampling is not that simple, essentially. This is some a special type of distribution that you need to compute and do that. I don't want to go through the details of them, but this is something that you can go, and this is actually, as I mentioned, you can have a course on reinforcement learning. But I have mentioned these ones. Why? Because the learning and game theory actually have lots of intersections. In particular, we have introduced, as I mentioned, this price of total anarchy. What was this price of total anarchy? Why it was interesting? Is that in the Nash equilibrium, what do they? The people are just doing best response to each other. Now assume that these people are doing no regret algorithms. Good. The people are doing no regret algorithms. However, note that, for example, when they doing no regret algorithms, so each person is doing no regret algorithms. But note that, for example, the traffic. So if I play this game and you play this game, and if we both go to the same route, then we are seeing more traffic on that. So this essentially, how I'm doing my no regret just by the knowledge, my knowledge, and you play it with your knowledge, and maybe third person is doing that. We have interaction through the network or some resources that we are considering. Because these are shared resources, and in some sense, like the things is that here, because these are shared resources, we compete with each other. So there is some game is going on. In some sense, my knowledge is not just knowledge of the distance from here. The knowledge also depends on who else are also in this network and playing this, going the same route, or at least part of my. That is the reason that actually game theory and no regret, though no regret is something that you can actually see, that it's easy to see that it is more general. If you have, in the Nash equilibrium, the regret actually is zero, the best response. You don't have any regret essentially, because given that all other people are doing that, you cannot do anything else. Now, this concept of essentially a no regret algorithm is that, now, what is the price of total anarchy? Price of total anarchy is that if these people are, each of them essentially doing this, there are several players, each of them are playing no regret minimization algorithms. You reach to some state that at that state, the regret essentially becomes zero. What would be the essentially what would be the efficiency or the social welfare in that case comparing to the optimal solution? So this is the one that combines essentially reinforcement learning or this no regret algorithms with price of anarchy. So, okay, if instead of best response, they are just doing no regret algorithm. And why the no regret algorithms are different? Because no regret algorithm, interestingly, in the Nash equilibrium, you may actually fixate it to one strategy. It might be a mixed strategy. But in the no regret algorithm, actually, you may alternate between two states. So you may never converge to one state. You may just alternate between these two. You may do this action and then you do this action and again do this action, do that. This may happen, but still you can say that in a no regret algorithm, when the regret becomes zero, if you consider the cost of your algorithm or the social welfare of the total things, comparing to the optimal solution, you can actually prove something good about it. And so this was the reason. And why do we consider now, as I mentioned, we obtain this result, then smoothness is something that the same way that you can actually prove, and we will discuss, price of anarchy, you can prove the price of total anarchy because of this smoothness property. Any game that has the smooth property, actually you can show that price of anarchy and price of total anarchy, everything is bounded. And we will give the bounds that is our pipes, essentially. That's the concept of this. This is the concept that I have mentioned for anarchy and for the smoothness, that we care about the smoothness. It's a very general way that you can actually prove some kind of bounds on the price of. And let's also, that I talk about this one, the regret, I wanted to mention this is also important thing for the no regret things. So this is also one important thing about it. So this is essentially the last thing that I want to talk about is no regret algorithm. It sometimes covers the base of this algorithm. And they mentioned the general type of algorithm, but you can of course read more and then get it, and you can have a class essentially on this one. That is beyond the scope of this course. Good. So the typical bound that we will get it for the regret is square root of t bound. This square root of t bounds is the common is the common and often optimal guarantee for cumulative RT of no regret algorithms. So what is that? We say that essentially the total cumulative regret algorithm grows at the rate proportional to the square root of the number of rounds. So there are so here consider this one, for example. Why this one is good? Because this, if we can show that it is a very typical thing, lots of this algorithm, for example, Thompson sampling or other this UCB, the bounds that they get, in different scenario, it might be different. But first, I mean, square root of t is good because it is sublinear. And when you take the average regret, the average regret would be R of t over t. That R of t is order square root of t over t, which is 1 over square root of t. And of course, as t goes to infinity, the average regret goes to 0. So, and this is very nice. For example, if your number of, say, if you have running this algorithm for 1 million times, then the regret that you will get, it is not close to 1 million. Because if it was close to 1 million, then it was a constant, it was not 0. It would be more closer to 1,000, which is the square root of 1. And of course, while your total regret still increases and you pay more rounds, I mean, that is very natural because you don't have the full knowledge. It still goes there, but it goes slower and slower. Essentially, the regret that you have is much slower than the number of rounds. So this is a typical thing that when you work, there are lots of bandit versions. This is a contextual bandits and other type of bandits as well. But a typical band that people essentially try to get it is a square root of t. Sometimes they can. There are some cases that still we don't know. For example, there are the best band that are t to the 2 over 3, not 1/2, but there are few instances like this for some kind of bandits because it can have different settings. But still, lots of them, the people will ask whether t to the 2/3 is the actually height bound or you can get a square root of t. So the people generally, they expect to get a square root of t. However, and this is, good. However, I want to emphasize that there are some cases that this there are, like, for example, if you have some kind of convex optimization, online convex optimization, a typical things would be a square root of t bound, and that's the best that you can hope for. There are some cases, for example, if it is something like called strictly convex or etc., sometimes the better bounds like order like t might be possible as well. But this is rare, essentially, that you can get the total things order like t. But generally, the total things would be a square root of t for lots of things. So you always try to find a square root of t because you know that, and there are some scenarios, the lower bound, that you cannot get better than a square root of t. So a square root of t is sometimes both upper and lower bounds, the tight things. They mentioned there are some cases that we don't know what is the type, but generally a square root of t is the one that the people conjecture about the things. And again, there are some cases that you may get log t, but these are rare in Islam. Good. So I think I covered the basic of no regret algorithms. And this is now the setting that we are considering here. This is the one that we discussed. Essentially, we have this pure Nash, mixed Nash, correlated, equivalent, and no regret. This no regret is this kind of easy learning algorithms. And the good things about them, this is also another issue, is that for when we consider the Nash equilibrium, one issue is that finding the Nash essentially might be hard. Or if the people are just, if the people do best response, it may take, the dynamic may take exponential time to reach that. But this kind of no regret algorithm, that when they are doing no regret at each rounds, actually these algorithms are the ones that converge generally fast, and they are very good settings, very practical settings. And there is some concept of equilibrium in some sense is there, because given that other people are doing this and this is the no regret algorithm that they are doing, you don't want to change yours. To read more about it, you may actually read this paper that I have mentioned. This is the paper that this is the paper in stock 2008. Was it, I think, 2008 or 2009? There's one paper, I think maybe it was, I think it was 2008, but anyhow, just check that one. Yeah, so that was 2008. This, the other things is Rock Garden essentially results in 2009. And if you go to the web page of the course, also there is this that we are using essentially. Rock Garden also has had a survey on these smooth games that we are talking about it. It's called Intrinsic Robustness of Price of Anarchy, and it talks about all of this Price of Total Anarchy, etc. But you can also go through this paper they mentioned. This is the one that we introduced it, and there are some nice examples here essentially, and we will motivate it why this is a nice thing, and we talked about this particular no regret algorithm and how we can do it. But here, Ragadan showed that actually you don't need to go prove something for Nash and pure Nash and mixed Nash and I don't know, a no regret algorithm separately. As long as you can have this kind of a smoothness, then you are in a good shape. Now, let me just go and then prove this one, no regret ones. This Price of Anarchy for this one. This is actually very three-line proof, essentially. Good. Let me just go down. Okay. So, what was the definition? So here we consider the game that we consider this congestion game. The people can take the different routes that we talk also about their corresponding no regret algorithms. The people take the different routes. And then the objective function is that, I mean, each person consider what is the total time that he has been essentially in the commute time, and you try to minimize that. And here, as I mentioned, consider the cost of the whole strategy S. It means that a strategy profile S, which is the vector of strategies, as the sum of the individual commute time for each of these given S. Note that it is important. It's CI of F. It means that when these people all play this S, and of course they are common resources that they may use together, and that this is the, if both of these people try to use the same route, then the traffic would be more for. So that's the issue that we will call it CI of S, and S is the strategy profile of everything. And this was the definition of smoothness. That is, the definition was that the CI of this, again, if you just change one person in SI to SI star, then the cost, and sum it over all of them. If you one by one, you will check, I will consider S, and then one by one, I will change the first one with S1 star, and see what is the cost in case. S2 with S star bar, what is the cost, and so on and so forth. And then sum it up. The sum should be dependent, essentially. Mu should be less than 1, and lambda should be greater than 0. It should be should be less than for these two numbers. In some sense, it is similar to this kind of, it is called convex combination. It's not quite convex combination, but in some sense, if you do that, then the still I can bound the cost of these new scenarios in the game. Now let's see why this gives essentially a good proof of anarchy, price of anarchy or anarchy. So if a game is lambda mu smooth, with lambda greater than 0 and mu less than 1, then each Nash equilibrium has at most lambda over 1 minus mu times that of an optimal solution. What is the meaning of that? It means that the price of anarchy is lambda over 1 over mu. Good. So let's see, the proof essentially. So assuming that lambda mu smoothness, cost of S, the total traffic time, is equal to individual traffic times, correct? Sum of the orbits. This is by definition. Now, since S, this is the important one. Since S is the Nash equilibrium, if I change in S, the i's component of this, if I change it with S star I, the cost can go only up. Why? Because this is the best response. Si was the best response. I just change it with an arbitrary guy, which is, in this case, S star I. Then I just use the definition of smoothness. So then would be lambda. I know that because of the definition of smoothness, this is at most lambda cost of S star plus mu times cost of S. And what is the cost of S star? Is the cost of optimum. So here I just do this one, so I know that this is less than equal to this. It means, by the way, cost is, this is equal to C of S. So then I know that the cost of S or C of S is at most lambda times cost. Just do the simple calculations. And because of that, so the cost of S, I can relate it with the cost of optimum. For example, using the proof that we have shown essentially, so one important thing, for example, for non-atomic congestion game, if you remember, we have the similar proof. We had this one for non-atomic games. If you remember, we had the C of F of Q, the cost of FQ. We proved it essentially using this kind of geometric things. We had some kind of geometry argument that we could show this one. And using that one, we could show that here, we could show the price of anarchy was 4/3, because then you can say that, yeah, here you get 3/4 of F of cost of equilibrium is less than cost of optimum, and then you get 4/3. However, in this case, also, if you can easily show that using the same argument, essentially, show that in that case, lambda is equal to 1 and mu is equal to 1/4. And price of anarchy, so this one that we got it through this calculation, you can actually do it just using this formula. This one is non-trivial. This part is non-trivial, how you can show that. Because that you need to show for different games, you need to show different, maybe different things. But this is a typical thing that you can show, and then you can get the 4/3 as the thing. And here, note that this one. Here, note that this kind of, in some sense, a smoothness is stronger than the concept of price of anarchy. Why? Because it's maybe more than needed in some cases. Why? Because here, when you try to get the price of anarchy, you only need to consider any Nash equilibrium here and the optimum solution. Good. You only need this smoothness for any S, for any equilibrium, and the optimum solution. However, this one actually says more generally, say for any pairs of S and S star, we should have this property. So in some sense, we only get for Price of Anarchy, we only use the case that S star is actually equal to optimum. And S is a Nash equilibrium. However, this smoothness for game is defined for every pairs of SMS. So in some sense, it's stronger things. But interestingly, we can actually prove for lots of games that we know, we can actually prove the Price of Anarchy using this one. Because now, actually, or in some sense, the proof that we are doing is really does not use the fact that this is a Nash equilibrium or the other one is S star. It's the optimum solution. There are a few games that we don't have essentially. We cannot prove the Price of Anarchy. For example, network formation games, if I remember others, we can go through that. For them, we don't have such kind of, like we cannot get it, at least, I mean, a few years ago, we couldn't get it using this kind of smoothness analysis, but almost all other things we can get it using this. And the good thing is that not only it works, the same arguments, you can prove that. So this theorem that we have mentioned, you have mentioned for Nash equilibrium, you can prove it also for the no-regret algorithms. A similar proof exists. And then it shows that if you have a smoothness, you can also give the price of total anarchy bundles. Good. So next time we will talk more about these conditions. We will give some examples. This is the minimization that we try to minimize the total cost, but we will consider also the cases that we are maximization problems, that you try to maximize the payoff of this thing. There are some games that is like that. And for them, essentially, we are still using this price of, essentially, this smoothness analysis. So, good, I stop here. Any questions? Good. So I think we will continue next time. We will finish this one smoothness game, and then after that, we have one session. We talk about another concept, market equilibrium. That is also like market clearance conditions, etc. That's another important things. And then we covered like lots of basic of this one. We talk about some other things like mechanism without money, essentially, or we talk about a few other concepts. These are basic concepts in game. And then, but just so we start the these things. So we should have 3 essentially presentations on not next week, the week after that Tuesday. And you just talk about your problem. But as I mentioned, try to mention something like 10-15 minutes, focus on one problem such that the people understand. That's super important. And we may have some interruptions, etc., because as I mentioned, this is for increasing the quality of presentations. That is my main goal here, is that I want that you will become essentially ready for research, or if you want to go industry, there's no difference. You need to do the same thing in almost all companies or things. When you present it, you need to have these rules that we discuss in class, essentially consider them very serious. Okay, so if there is nothing here, let's stop shares, and then we can finish everything.